Okay, so welcome to Photoelectric Effect for Physics 30. So we're going to actually start off with a little bit of a money analogy. Now, if I'm coming back from a trip to from the United States, and I have a $10 bill left over. Well, I can't use that in Canada, and so I'm going to go to the bank. Now, the posted exchange rate says it's 1.30 Canadian for every US dollar. So how much should I get back? Well, what I'm expecting is that I'm just simply multiplying this by 1.30, and I'm expecting $13 back. But I expected $13 back, but in reality, I only get $11 back. Where did that toonie go? I want my toonie, want my full value. But in fact, I did receive all that money. It's just that the bank kept $2 in exchange for the work they did in making that currency exchange. And that makes sense. They did post the fees there, and they said that we charge $2 for every currency exchange, and therefore I only get 11 back. What does this have to do with the photoelectric effect? Well, the photoelectric effect is that emission of electrons when electromagnetic radiation, such as light, hits a material and electrons are emitted from it, right? So we've got electromagnetic radiation coming in and we've got electrons coming out, right? Electromagnetic radiation coming in and we've got electrons coming out. It was discovered like this, where you have light coming in on a surface and then the electron comes across to finish, right? You got that electron coming across here as the EMR comes in, and it's detected using the current and voltage of the system. So if we think about the incident light as the incoming currency, that would be, by our analogy, the US dollars. But really what we're talking about is the energy, how much energy we've got coming in from that electromagnetic radiation. The work function is what we call the exchange fee, right? The bank fee, the money, right? That's the energy to lift off electrons. And the emitted electron is what I get back. That's the energy the electrons have afterwards. So if I put in 13 units of energy, but the exchange fee is 2 units of energy, afterwards those electrons would have 11 units of energy remaining. So what is the energy of a photon that has a wavelength of 5.20 times 10 to the 2 nanometers? Well, we've seen this before. It's hc over lambda. So this is going to be 6.63 times 10 to the negative 34 joule seconds, Planck's constant. 3 times 10 to the 8 meters per second is C. And we've got 5.20 times 10 to the negative 7 meters as your wavelength. The energy of the light coming in is 3.2 times 10 to the negative 19 joules. However, when this shines on a surface, not all of this could go to the electron. Some of it has to get that electron off the surface first, that work of moving the electron from electromagnetic radiation to the electron. There's some work there, and that's like our banker's fee. And if we did not have a frequency high enough, meaning enough energy, no electrons would be emitted. Now, what we do is we call that essentially the fact that there's a work function. Right? So if you've got electrons above threshold, violet light having a shorter wavelength, higher frequency, therefore more energy, it's able to produce these photoelectrons coming off the surface. Where photons below the threshold, such as yellow light, longer wavelength, lower frequency, lower energy, they do not emit one at all. Right? Coming back to our money analogy, if the bank always charges exactly $2 an inch, right? This is what we call a flat fee. What do I get if I have $20 US to exchange? That would be 26 Canadian dollars. Well, I would get 24 back, and the bank gets 2. What if I only bring $1 back? Well, bank takes it all. Now, if I went to the bank 20 times with this $1 bill, so I took 20 trips to the bank with a $1 bill, they would charge me that flat fee every single time. But if I go once with that flat 20 bucks, there, each trip to the bank is like a photon. And this was the discovery of that kind of or verification of Planck's quantum hypothesis that in fact light did travel in distinct bundles. Right? Each trip to the bank is equivalent to one photon coming into the bank and trying to get some money back or releasing an electron. If I don't have enough money to lift it off, doesn't matter how many times I bring it in, each time is an individual transaction. Let's come back here. So, for example, here, each one of these photons coming in is not enough. It doesn't matter if it comes in 10, 20, 30 times. If it comes in 20 times, each time there's not enough to bring an electron off. Where if I go once with more energy, there is enough to bring it off. So to get that sufficient energy, we call it the work function, has to have a certain frequency, that's H frequency, and that's really just very similar to what we've seen with Planck's hypothesis, E is equal to HF. It's just the work function has to meet this minimal amount. Right? Any frequency higher will have more energy and therefore will actually emit electrons. Right? AKA cover the banking fee. So if a surface has a work function of 0.85 electron volts, what is the threshold frequency of this surface? Okay, well, that work function is equal to hf naught. Now the work function we know is 1.8 electron volts, so for h, instead of using our 6.63, we're going to use our 4.14 times 10 to the negative 15 electron volt seconds. And the reason for that is we're keeping the units consistent. That's on our formula sheet. It's easier than to translate this. Okay, we're looking for that frequency, which means we're going to divide both sides by 4.14 times 10 to the negative 15. The result is 4.5 times 10 to the 14 hertz as being your threshold frequency. So what does that mean? That means anything with a frequency higher than 4.5 will release electrons. Anything with a frequency lower than 4.5 times 10 to the 14 hertz will not. It will all be sucked up. All that energy is basically sucked up in the transaction fee that the bank keeps, or it goes to the electron, but the electron does nothing with it. So I would like you to pause the video, give this one a try. Right? What is the work? It has a work function of 3.515 times 10 to the negative 18 joules. What's the threshold frequency? Okay, welcome back. In this case here, work function is still equal to hf naught, or the threshold frequency, but we've been given the energy in joules. So we use Planck constants in terms of joules to find that threshold frequency. And again, this is really just saying what minimum amount of frequency is required in order for electrons to come off of that surface, right? Anything higher will release electrons. Anything lower would not release any electrons. In order to figure out how much energy the emitted electrons have, we supply an external voltage to stop them. Right? The idea here is that if you want to figure out how much there is, we take that stopping voltage, the energy required to stop them, in order to kind of give a measure of the electrons, and we do that within the circuit. If you remember this slide, here we've got, again, a voltage that acts against the electrons, so we're trying to stop them, right? So we've got a voltage working the other way to stop the electrons, and once you got everything running, you ramp this up until you get to the point and measure how much it takes in order to stop the electrons flowing. Another diagram of the same thing. You've got electrons coming here, or sorry, electromagnetic radiation coming in here. You've got electrons coming out, and you're detecting with a voltage meter. However, you then set up a system to try to stop them. Once you see that this reaches zero, you know that you've in fact stopped all the electrons coming through. Right, and so the formula you'll see on your formula sheet is this one. EK max is equal to QV stop. Right, it's just simply the charge of an electron multiplied by the voltage will get you the energy of the electron. So what is the stopping voltage if you've got an electron that has 2.17 times 10 to the negative 18 joules of energy? Well, we know this formula. The energy of the electron is 2.17 times 10 to the negative 18. The charge on an electron is 1.6 times 10 to the negative 19, and we're looking for the voltage. Okay, So dividing by that 1.6 times 10 to the negative 19 will get you a stopping voltage of 13.6 volts. Now, so in order to stop the electrons, it took 13.6 volts of energy to do this. Now, interestingly, if you use this formula and you say the charge is 1 electron, the units here are electron volts, which gives you the energy in electron volts. Right? So charge being 1 volts, the volts that's used to stop actually gives you the energy directly of the electron volts. So give this one a try. What's the stopping volt of an electron with 1.8 electron volts of energy? Pause the video, give it a try. And welcome back. And if you were absolutely sure, you probably didn't even need to pause the video, you just said, well, it's 1.8 volts, Mr. Dunbar. But in fact, that's what it is. Because all you're doing, the charge, instead of using 1.6 times 10 to the negative 19 coulombs, you're just saying it's 1 electron divided by 1 electron. So the money exchange formula is essentially the input value, input energy, is equal to the work function plus the energy of the electron, money to me. Right? So the input value is that electromagnetic radiation energy, the work function being that phi, money to me. And so this formula is used for the money coming in. E is equal to hf, or hc over lambda. We know that from Planck's quantum hypothesis. The money coming to me is evidenced by the electrons. We use Ek max is equal to QV stop. And the work function is here, figuring out the phi for the surface. Now, each surface will have a different work function. It depends on the nature of the atoms within there, so we have to calculate that each time. Right? Incoming photon energy equals work function plus kinetic energy electron energy store of the electron. So let's take a look at another example. Electrons are ejected from a photoelectric surface with a maximum energy of 2.60 times 10 to the negative 19 joules when blue light is on there. What is the threshold frequency of the material? Well, we can figure out the amount of energy we've got coming in, right? So if we think about what we've got coming in, that's E is equal to hc over lambda. We've got the wavelength here, speed of light and Planck's constant we know. And so what we've got coming in is 4.97 times 10 to the negative 19 joules of energy, right? I should probably put in my numbers here just so that you can see where I'm getting that from. So that's the amount coming in on the electromagnetic radiation. How much is coming out, we know, is 2.6 times 10 to the negative 19. So what's the phi? Well, if I subtract the two, we see that that work function is going to be 2.3725 full numbers times 10 to the negative 19 joules. That's the phi, or the work function. And now that I have the work function, I divide that by h. And find that the work function is, the threshold frequency is going to be 3.75 times 10 to the 14 hertz. Okay, one more. Aluminum has a work function of 4.08 electron volts. What's the maximum speed of the electrons emitted if it's illuminated with a 125 nanometer source? Well, here we can figure out how much we've got coming in again. E is equal to hc over lambda. H is Planck's constant, we know that. C is speed of light, we know that. Lambda is this, the incoming source. And when you calculate that, you should find that this is, now I'm going to calculate this with 1.4 times 10 to the negative 15, keeping it in electron volts. 3 times 10 to the 8, all divided by 1.25 times 10 to the negative 7. And what we find here is we got 9.936 electron volts of energy coming in. The work function being 4.08 means I'm going to get 5.856 electron volts out in the form of the electrons. Well, to find the speed, I'm going to need to actually still convert that into joules. It's 1.6 times 10 to the negative 19 joules for every electron volt. And so that is going to get us 9.3696 times 10 to the negative 19 joules. That's going to be equal to 1/2 mV squared. So 2 times that energy divided by mass, all square rooted, will get us the velocity. And that velocity is equal to 1.43 times 10 to the 6 meters per second. Right? 2 times 9.3, I'm going to round that to 37 times 10 to the negative 19, all over the mass of the electron, 9.11 times 10 to the negative 31, all square rooted, got us the velocity. That's where I'm getting that number from. So we're going to close off this video with a quick look at the photoelectric effect overview, but thank you for watching.
His theory of relativity and the Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. And when technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions, so he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.